So what we are interested in about, if you want to use a device as an amplifier, we are interested in two kinds of characteristics. One is transfer characteristics, the other one is output characteristics. And we discussed that most amplifiers that we will be building are 3-terminal devices. So, and also we said most of the amplifiers that we are building are transconductance amplifiers, which means the current between these two terminals, the current between the output terminals is dependent upon the voltage at the input. So then it's a transconductance, a transferred conductance from input to the output. So the characteristics of the output current to the input voltage is what we refer to as transfer characteristics. And the output current to the output voltage is what we call output characteristics. Eventually, our goal is to derive this transfer characteristics for the amplifying device of interest. And we also discussed one very important thing, especially about output characteristics. What did we say is that if you have a device of this type, so let V here, V out is the output voltage, and here I out is the output current. If this output current is independent of V out, if the output current happens to be independent of V out, but rather depends upon the input voltage, so then we said the graph will look something like this. So I'm changing the input voltage, the current is increasing, it might increase or decrease, but here in this example it is increasing. But the output current should be independent of the voltage at the output voltage. It should actually be independent of the output voltage. Now, if I can build a device like this, so what kind of a device is this? I mean, what kind of a model is this? The output current is independent of the output voltage, but it depends upon some input voltage. It's a transconductance amplifier, a voltage controlled current source. So if you have a voltage controlled current source, and if I connect a resistor at the output, then we said I can realize an amplifier by choosing an appropriate value of the resistance. If I choose the transconductance GM of this amplifier times the resistance GM times RL to be greater than 1, then I have voltage amplification. In addition to that, you should be drawing little to no current at the input. If you are drawing little to no current from the input, then you will end up having a huge power gain. So that's the whole idea behind all these amplifier structures. And I discussed one very important point about a MOSFET. I said the idea of MOSFET is a field effect device. It had existed for a very long time, from 1920s. In fact, at mid-1920s is when the idea of a field effect transistor. So essentially, you have a semiconductor. You'll have a block of semiconductor. The idea was to apply an electric field. So apply a voltage at a distance, and this electric field is supposed to penetrate the semiconductor and bring electrons closer to the surface. So if I apply a positive charge here, it's going to draw electrons closer to the surface. Then I'll apply a voltage between these two terminals of the semiconductor, and I'll have a current generated between these two terminals, and the value of the current will depend upon the voltage that is applied or the field that is applied. So that was the idea, but there was a problem that these field lines were not penetrating the semiconductor to bring the electrons to the surface. So that's when they introduced an oxide, the problem was resolved. In between the metal and semiconductor, when they introduced an oxide, that problem was resolved. The field lines could penetrate and then electrons could be brought to the surface. Now, this again, like most discoveries, so they had given up on MOSFET in 1950s. So this was the engineers at Bell Labs who had chanced upon this idea again. So while they were experimenting, the same way a point contact transistor is also an outcome of rigorous experimentation, MOSFET is also an idea which was born similarly. So they had given up in 1950s. They thought BJT is the way forward. Even though MOSFET as an idea looked good, so as an idea it was simple. You bring the electric, you apply a voltage at a certain point away from the semiconductor, draw the electrons closer to the surface, and you will have some kind of a surface conduction. And between two terminals, if you create two terminals here, you will have a current flowing between these two terminals that will depend upon the field that you are applying or the voltage you are applying on this metal. The only problem was, as I said, the field lines were not penetrating the surface. So at that time, Bardeen had given an explanation for this, and but then later, when they introduced an oxide in between, the problem of the surface effects, the problem was called surface effects, where the field lines were not penetrating, was resolved. Okay, so that's when the metal oxide semiconductor field effect transistor. So that's why the word MOSFET originated from there. And from once MOSFETs were introduced in 1960s, today they are the most manufactured human invention in the entire history. I gave you an example. You count every matchstick ever manufactured. So that's like fire and wheel. Fire and wheel are the one of the most fundamental and oldest inventions of mankind. You count the total number of wheels ever manufactured in the history of mankind, or count the total number of matchsticks ever manufactured. The number of MOSFETs will be more than all of that. Okay, it will outcount any of that invention. Now, what we will do here is that we will try to show very briefly at an intuitive level that the MOSFET behaves like a voltage controlled current source, which means the output current. So we will try to derive an output characteristics and show that the current at the output will be independent of the input voltage or the voltage that I'm going to apply, independent of the voltage between these two terminals, which is the output voltage, for a range of values. Okay, so that's what we already showed, that for a BJT. In a BJT as well, the output collector current is independent of collector to emitter voltage in a certain range of values. So we said if you can get a characteristic like that, then we know in theory we can build an amplifier. So very briefly, we'll look at the output characteristics of a MOSFET. So before, the structure of a MOSFET. A MOSFET has a semiconductor. So this is the semiconductor. So the whole idea is to have a semiconductor and create a surface carriers. Okay. So and we have a metal, which is where we will be applying our positive voltage or negative voltage. So this is a MOSFET. So typically we apply a positive voltage. And then in between we have the oxide. So this oxide, again, I told you the reason why it was introduced was to resolve the problem of surface effects. For the field to penetrate the surface, you needed that. So this oxide, you take silicon, oxidize it, you get silicon dioxide, which is a good insulator. So I gave you an example: insulator, semiconductor, and conductor. What is the fundamental difference between all the three? What distinguishes them? So you can you speak in terms of number of carriers available for conduction? Yes, the number of carriers available for conduction distinguishes them. For an insulator, it will be several orders smaller than semiconductor, and for a conductor, it will be several orders. The number of carriers available for conduction will be several orders more than the semiconductor. Okay, so that's what we discussed before. So you have a metal, oxide, and semiconductor. So the structure will look like this, and we have two more terminals, which will be N plus regions, heavily doped N plus regions. So the reason why this is N plus is that we are expecting electrons to crowd near the surface. So if this is an N plus region, then you will have electrons can easily flow from this semiconductor into the output terminals. Okay. So if it's a P substrate, if it's a P pocket, if I create small P pockets here, will there be conduction? If the carriers are electrons, they cannot travel in a P region, right? So you need an N plus region for conduction to take place. So that's why they are N plus regions. So when your channel is formed, so meaning if you apply a positive gate voltage, electrons will crowd near the surface. So you will have a continuum of electrons in the surface region. The whole surface from this source terminal to drain terminal will be one continuous conducting channel of electrons. Okay, so we'll briefly discuss how that happens, but this is the structure of a MOSFET. You have a metal terminal, a semiconductor, and oxide in between, and you have two N plus regions, which are the drain and source terminals. So this is we can see the drain to source as the region where current flows. The terminals between which the current flows, and we have to show that this current, which is flowing from drain to source, depends only on gate voltage and not on drain to source voltage. If we can show that it happens in that, the device behaves in such a way, then we know that the device can be used as a amplifier. Okay, so that's the whole idea here. Now also remember, because this is an N plus region, this is a P substrate, there is a parasitic diode which is automatically formed. By its construction itself, you have two diode structures formed automatically. Okay, so now I'll first discuss about the symbols that you'll be using for MOSFET. So in a MOS region, as I said, for an N-channel MOSFET, it's called as an N-channel MOSFET. If you apply a positive voltage at the gate, we said electrons crowd near the surface. If electrons crowd near the surface, then we have one continuous channel between drain and source. So we say in that point when the electrons crowd near the surface, we call it as inversion. And such a device is what we call enhancement mode device. So your increase of gate voltage enhances the channel. So it's called as enhancement mode device. So the symbol for the enhancement, it's a 3-terminal device. In fact, there are 4 terminals here: drain, source, and also bulk. The semiconductor potential is the potential of the semiconductor, we call it as the bulk. Okay, that's the 4th terminal. Now the symbol for a MOSFET, you will show this dashed lines here. The dashed lines here show that when there is 0 gate voltage, there is no channel. When the gate voltage is 0, there is no channel between the drain to source. As you increase the gate voltage, channel is formed. So that's why these dashed lines indicate that. So there was no channel for an enhancement mode MOSFET is represented by 3 dashes here. And then the 4th terminal bulk is shown as an arrow pointing inward. Historically, the symbol comes from this. So if you look at a conducting MOS device, N-channel MOSFET, the bulk terminal is a P-type semiconductor, and the channel is N-type. So if you see, there is a diode that's formed this way. So the arrow indicates the diode formation. It's just to indicate the channel is N-type. So from substrate to N-type, the arrow indicates that. So this is how the symbol of an enhancement mode N-channel MOSFET is drawn. Similarly, for a P-channel, I haven't shown it, probably I don't have a symbol for P-channel. So you will have source. So we'll show 3 terminals. So this will be source, this will be drain, and gate terminal. This will be your 3rd terminal is gate. And because for a P-channel, you start with an N substrate, the arrow mark will be pointing outward. So the channel will be P-type and the bulk will be N-type. So the diode will be in this direction. So the arrow mark will be pointing outward. Okay, so that's the symbol for a P-channel MOSFET. The other symbols we use for N-channel MOSFET is a 3-terminal symbol where we simply show the arrow towards the source. So we show the arrow towards the source. That's to indicate the direction of flow of current. Okay, this is a 3-terminal MOSFET. In a 3-terminal MOSFET, generally drain and source are, bulk and source terminal are shorted. Bulk and source terminal are shorted. Then we just represent it by a 3-terminal model. Okay, so in your the software cadence which you are using, so they'll directly show a 4th terminal this way. But this is the history of symbols. So if you are probably going to show it as a symbol, this is how we'll show it this way to show the bulk is a 4th terminal, or we might directly give you this one. Here it's assumed that source and bulk are tied together. Okay, so this is the 3-terminal model of a symbol of a MOSFET. So now we will very briefly look at the physics of the operation of MOS device. So what in our mind, what are we trying to show is that the drain to source current, the flow of current between the drain to source should be for some voltages at least independent of drain to source voltage. If that can be accomplished, then we say that an amplifier can be built out of this device. So first, I'll start with the simplest voltage application. So first I'll connect the bulk terminal to ground. Bulk is at ground. I'll also connect drain and source at ground. Both the drain is at ground, source is also at ground. So remember, these two PN junctions are now off. So there is no conduction between here. There is no conduction here. Okay. So that's why there is a PN junction. So you will have some space charge region or depletion region. So right, the moment you have a PN junction, you will have at the metallurgical junction, around the metallurgical junction between the P-type and N-type semiconductors, you will have a built-in region or a space charge region. So this will be the region of immobile charge carriers. Okay, so that's the structure what I've shown here. Now I'm going to apply a small positive voltage at the gate terminal. Now what will happen when I apply a small positive voltage is that if I apply a small positive voltage, electrons will start. See, how am I going to apply? I'm going to apply a voltage source connected this way, a voltage source connected this way. So when I'm applying positive charge, I can conversely say that I'm removing electrons out of this. right? If I'm applying positive charge on the plate, that's equivalent to removing electrons. So to account for the return path, I have to supply electrons back here to the bulk terminal. Now these electrons which are supplied into the bulk terminal will slowly move towards the surface, because these electric field lines which are penetrating this semiconductor are drawing these electrons closer to the surface. See, there is an electric field which is present because of these positive charges on this plate, which is penetrating the semiconductor, and they are drawing the electrons closer to the surface. Now these electrons, see, understand these are electrons, right? Electrons, what kind of carriers are they in a p-type semiconductor? Are they minority or majority? In a p-type semiconductor, an electron is a minority semiconductor, minority carrier. So which means a minority carrier, if it is traveling in a majority carrier world, see, this is an electron which is traveling in a majority carrier world, they will constantly undergo recombination, because it's an electron is traveling in a whole field world. So oftentimes it will undergo recombination, and then there will be a thermal generation, the electron will be liberated out, and then again this electron will constantly drift towards the surface. It will slowly move towards the surface. At the surface, you have silicon dioxide interface. You have a silicon and silicon dioxide interface. Now that's a barrier electron cannot cross. So the electron will stay near the surface. But this is a p-type semiconductor, right? So, but there are already a lot of holes near the surface because it's a p-type semiconductor. So this electron will first recombine those holes, and it will create a region of, because as I said, this is a p-type semiconductor. It's a trivalent impurity, right? It's, for example, imagine a boron atom. So silicon forms it has 4 valence electrons, and it forms 4 covalent bonds with its adjacent silicon atoms. If you replace one of those silicon atoms with boron atom, it's going to have one hole, one vacancy. Now this electron which is going to go to the surface will fill that vacancy. Once it fills that vacancy, boron acquires one extra electron, and it becomes a negatively charged ion. Okay, so what happens near the surface is that you are going to have immobile negative charges as these electrons are drifting towards the surface. Now I'm going to increase the voltage further, the gate voltage further. I'll keep on increasing it. Once you have sufficiently recombined with most of the holes in the surface, after that, your surface it was a p-type semiconductor. At some point, it will look like an intrinsic semiconductor. If you recall, when your doping concentration becomes, if you dope your let's say you start with a p-type semiconductor, you must have heard of something called compensated semiconductors. If you start with a p-type semiconductor, with say Na being your doping concentration, and keep on adding electrons to this, donor atoms to this. What happens when your donor atom becomes equal to the acceptor atoms? It becomes intrinsic, right? What happens to the Fermi level? What happens to the Fermi level? Look at it from Fermi level point of view. You have conduction band, you have valency band. This is conduction band, this is the valency band. Previously, Fermi level was exactly at the center. Assume that it's close to the center. When you dope it with dopant atoms, when you dope it with acceptor atoms, which is your p-type semiconductor, your Fermi level will move closer to the valency band. But when you keep adding Nd, electron, more and more donor atoms, your Fermi level will start shifting upward, and it will coincide with the intrinsic semiconductor's Fermi level. What does it mean? Every excess, see, for example, every excess donor atom you add has an extra electron. That electron will go and neutralize the boron atoms that you have added. So there will be equal number of negative boron ions and positive phosphorus atoms. So net, the semiconductor will be neutral. So it will look like you have really not contributed to any extra electrons or extra holes in the system. It will look like an intrinsic semiconductor. So the surface will first become intrinsic because your electrons will neutralize most of the holes at the surface. After that, any extra voltage, as it brings more and more electrons to the surface will now become an n-type semiconductor. So at that point, we say the surface is inverted. It's a p-type semiconductor. First it became intrinsic, and then it became an n-type semiconductor. But the surface has now become inverted. So then a channel is formed between drain and source. It's a continuous channel formed between, because it's a region filled with electrons. So we can say that it's like a continuous channel formed between drain and source. And the voltage for which it happens, this condition where the surface concentration becomes closer or greater than the acceptor ion concentration in the bulk. When the electron concentration here becomes greater than the hole concentration in the bulk, we say the device is in strong inversion. And the gate voltage corresponding to that is called threshold voltage, VTH. So if your gate voltage is greater than this, you have the surface electron concentration greater than the bulk hole concentration. Now what after that? Now what I'm going to do is that I'm going to apply a small voltage between drain and source. I'm going to ground the source terminal and I'm going to apply a drain voltage. So here you have to just understand one equation. I'll tell you intuitively, the surface charge, the charge which is going to come to the surface depends on two things. It's equal to oxide capacitance times Vg minus Vt, that's your threshold voltage, minus V of x. So V of x is your, x here represents your horizontal surface potential. That should make sense because look at this result. As you increase your gate voltage, more electrons would come to the surface. So you should expect the charge, which is this charge near the surface, is called inversion charge. It's going to increase. In addition to that, if let's say I increase my drain potential, if I increase my drain potential, what am I doing to this PN junction? Bulk is at ground, drain voltage is higher. So the PN junction is getting forward biased or reverse biased? Reverse biased. This PN junction is getting reverse biased. If the PN junction is getting reverse biased, what will happen is that the depletion width will increase of this PN junction. So this surface near the drain, it's going to lose some electrons because it's going to repel away some electrons as the depletion region is going to form there. So intuitively we can see it's going to reduce with the voltage, surface voltage, and it will increase with the gate voltage. So this is the general expression for the surface charge or the inversion charge in a MOSFET. Now I'm slowly increasing this drain voltage. So I'm looking at the drain side of the MOSFET. I'm slowly increasing the drain voltage. But this drain voltage is such that there is still some charge present near the drain terminal as well. Now look at this. This is an entirely conducting region. This looks like an N-type semiconductor. So whenever you have an N-type semiconductor and you apply a voltage across it, how does that behave? What is the behavior of an N-type semiconductor? If I take an N-type semiconductor, a bar of N-type semiconductor, and apply a voltage across it, what will be the behavior of an N-type semiconductor? What can I expect? How will the current change? It will behave like a resistor, right? It's an N-type semiconductor. It's like a conducting metal. It's like a conducting material. So if I apply a positive voltage, then the current is going to increase. And the current will increase linearly. So this, I think we have derived this result in physics of semiconductor devices as well, where we show that an N-type semiconductor obeys Ohm's law, which means the voltage across, if you apply a voltage, the current that's going to flow will be equals V by R. And we discussed how to find the value of the resistance in an N-type semiconductor. The resistance is given by L by sigma A. And for an N-type semiconductor, what does the conductivity depend upon? It depends upon mobility, the number of carriers available for conduction. What else does it depend upon? And charge, NQ mu. Is that right? The conductivity of this depends upon NQ mu. N is the number of electrons carriers available, NQ is the total charge available, and mu is the mobility of the electrons. Mobility tells you how fast your electrons can drift in the presence of an electric field, applied electric field. So if your number of available carriers are more, you will have a high conductivity for that region. So what will be the conductivity of the depletion region? So if whenever you have depletion regions here, what do you think will be the conductivity of the depletion region? In depletion region, are there any carriers available for conduction? Zero, right? The conductivity of a depletion region is 0. So I can say the resistance of the depletion region is infinity. Keep these 2 points in mind. We'll be able to understand the MOS basics very simply. So first, for small incremental values of drain voltage, between drain to source, the current is going to slightly increase as you increase the drain voltage because there is an horizontal field now. See, previously these electrons were mobile electron concentration near the surface. But unless you apply a horizontal field, these electrons are not going to drift, right? For them to drift, you need to apply a horizontal field along this direction. Vertical field, the gate vertical field is necessary to bring the electrons to the surface. Horizontal field is necessary for the electrons to drift from source to drain. So then there will be a current to the device from drain to source. So these electrons are now going to drift with the application of the drain voltage. So when the electrons drift, there is going to be a drift current. So that's what I have shown here. So your current, I'm plotting the drain current with respect to drain to source voltage. The source is at 0 volts. Vs is at 0 volts. Bulk is also at 0 volts. So because both of them are at 0 volts, I'm assuming I'm only showing Vd here, but it is actually Vds. It's Vds here. I've only written it as Vd, but both of them, your source is at 0 volts. So your drain current will increase linearly with drain voltage. But what did I say? The channel charge is now going to be lesser on the drain side, because we said it reduces it's proportional to Vg minus Vt minus Vd. At the drain side, it's going to be minus Vd. It's going to reduce with, so it is proportional to Vg minus Vtn minus V drain. So it's going to reduce. So your channel charge at this drain end is going to reduce. Now look at it this way. I'm going to draw the channel here. So what I'm going to do is that I'm going to draw this exaggerated version of the channel. Look at this. This Mosfet is a 3-dimensional device. So it's going to extend this way on all the 3 dimensions. So this is called width of the Mosfet. So this is your Mosfet's width, and this is your length of the channel. So W is your width of the Mosfet, L is the length of the channel. Now, as an engineer, these are the 2 design parameters which you can use to control or to design an amplifier. So what will happen on the drain side, as your drain voltage increases, the charge reduces near the drain side. So now I'm going to plot the charge concept, the surface charge. I'm going to show you a 3-dimensional view of the surface charge. See, previously the surface charge looked something like this. It was like this previously. This was at Vds equal to 0. When there was no drain voltage, it was like a rectangular box of charge. But now what's happening, as you increase the drain voltage, on the drain side, the charge has reduced. So this is your region of occupancy by your electrons. This is the surface electron. This is your source end. This is your drain end. Now we know resistance is nothing but rho L upon A, or I can write it as L upon sigma A. The conductivity of this region is same, length is same, but what is reducing here? Can I say the cross-sectional area is reducing here? See, the cross-sectional area is reducing out towards the drain end. What do you think will happen when the cross-sectional area reduces? Look at this resistance. What will happen to the resistance if cross-sectional resistance reduces? Resistance increases. So I will use the word incremental resistance. So for any excess increase in Vd, the resistance is going to incrementally increase. If resistance incrementally reduces, current will be increasing, but the slope with which the current will increase will reduce. Okay, the incremental resistance is decreasing. So can I say incremental conductance is increasing or decreasing? So sigma, I'll write G is decreasing, R is increasing. So if you look at this graph here, that's what this graph tells you. As you increase the current, the slope of this graph is reducing. What is the slope of the graph? What does it give you? I versus V. What does the slope of the graph give you? The incremental conductance. 1 by R, which is conductance, it gives you the incremental conductance. And we just said that because the cross-sectional area is reducing as you increase Vd, the incremental conductance will reduce, which means the slope with which the current will increase will reduce. So it's slowly reducing. So at some point, so I've shown here, this is the 3-dimensional view of the Mosfet, just so that you know it's clearer to you. So this is your width of the Mosfet. On this axis, this is the width, and this here is your length of your MOS device. Okay, so this is the 3-dimensional view of your MOSFET. This is an N-type. This is an N-type semiconductor or N-channel semiconductor, N MOSFET, and this is P MOSFET. Okay, I'll just come back to this now. So what we are looking at is we are looking at the channel, just the conducting part of the channel. No, I'm increasing the drain voltage. I'm interested in knowing how my drain current is changing. Okay, so that change in the drain current can be obtained by the knowledge of incremental resistance. Let's see, the graph is nothing but if I'm plotting a graph ID versus VD, if I know if I know the profile with which the current is increasing or decreasing, then I will know the incremental resistance. So that will tell me how much my current is going to increase for an extra increase in my drain voltage. Is that fine? So the reason why are we trying to understand incremental or even looking at incremental resistance is to understand what will be the increment or change in the drain current for a change or an increment in the drain voltage. That's what we are looking at. Okay, so now we'll come to a point. What happens here is that as you keep increasing the drain voltage, when your drain voltage becomes, you see what is your inversion charge at the drain end? Vg minus Vtn minus Vd. Now when your drain voltage becomes equal to Vg minus Vt, when it becomes equal to Vg minus Vt, or I can, since source is at ground, see here I'm assuming source is at ground, so I can say Vgs minus Vtn and Vds, I can represent inversion charge as Vgs minus Vtn minus Vds. So your drain voltage will be Vgs minus Vtn. When your drain voltage reaches this value, the channel charge at the drain end will become 0. When the channel charge at the drain end becomes 0, what is the incremental resistance at that point? The cross-sectional area has come to 0, right? The cross-sectional area has become 0. So rho L by A will become infinity. So the incremental resistance will become infinity. If the incremental resistance is infinity, what does it mean? What does it mean to the IV graph? Even if I am changing my voltage, will there be a change in the current? Incremental resistance is increased. There will be no change in the current. That's what it means. So even though the slope here becomes 0, incremental conductance becomes 0, incremental resistance becomes infinity. So after this, the current is flattening out. So we'll see what happens after that. So now I'm going to increase my drain voltage further. I'm increasing it even more than the saturation voltage, which is VD sat. When I increase it, the end region will now start depleting. I mean, around the end region, you will start having depletion charge. You will have immobile. So here this will be P region, so you will have immobile negative charges here. There will be more reverse bias for this P junction, and it will start depleting the carriers, the mobile carriers around the end region. So now you have to visualize, look at this. The electron is drifting here. It's drifting here till this point. After this point, you have immobile negative charges and positive charges on the n side. So there is a very strong electric field in this direction. What do you think is going to happen to the electron at this junction, at this surface, at the end of the surface? What will happen to that electron? See, there is a strong electric field here. So it will be quickly swept across to the drain side. Immediately swept away. It will be immediately swept to the drain side. There is a strong electric field. It will quickly push it to the drain side. So that's what happens to this electron, which is going to drift. It will drift and come to this region, and it will be immediately swept across. So now look at this. There are two regions here. The electron is traversing two regions. It's traversing a region where there is a channel of conducting electrons. Then it is also traversing a region which is composed of immobile charge carriers. Okay. So this region, now I'll model this region as two resistors. So this is the channel. I have written here as from source end to drain end. I'm modeling it as, on one side you have a conducting channel, which is where electron is going to move, and when the electron comes here, it will be swept across this region. And here you have space charge region. So I've modeled them as two resistors in series. What will be the resistance of this region? Space charge region. What will be it's a non-conducting region, right? It's a charge. It's a region filled with depletion charges. What will be the conductance of that region? Resistance of that region is infinity. Okay. So the resistance here is infinity. The space charge region resistance is infinity, zero conductivity. So now if I apply any excess drain to source voltage, incrementally if I'm applying drain to source voltage, I have two resistors. Which resistor will take major chunk of that excess voltage? The space, right? The one which is infinite resistance will take up most of the voltage because they both are in series. There will be potential division, and most of the voltage will drop across the space charge region. So which means any extra drain voltage you are applying will actually drop across this region, and the voltage across this region, the conducting region, will remain more or less the same. That voltage will not change at all. Now I'm going to make another assumption quickly. The assumption is that the length by which this channel is reduced, I'll neglect it. It's very small. I'm going to neglect that. If I neglect that, the voltage across this region is fixed. The length is also fixed. Can I say the current is fixed? Right? It's just drift electron. The current is mainly determined by electron drifting in this region. So in that region, the current. So therefore, any extra increase in the drain voltage will cause no increase in the drain to source current. So the graph will just flatten out like this. Now I have exactly built a device which is giving me an output characteristic where the output current is independent of the output voltage. So therefore, I can in theory use this device as an amplifier. Now look at this. If I increase my gate voltage, I'm going to get different graphs like this, because the inversion charge itself is going to increase. When charge increases, let's say I increase my gate voltage. If I increase my gate voltage, you will have more charge to begin with. The graph will look like this. You will have more charge to begin with, which means you will have more current. So if I increase gate voltage, current is going to increase, but the graph will look the same. But the point where the saturation occurs will slightly change. But what I have accomplished here is a voltage controlled current source. Current is varying between drain and source, and that current is independent of the gate voltage, drain to source voltage, but it only depends upon a third terminal, which is your gate terminal. So therefore, this device now can be used as an amplifier. So that if you now vary the drain to source voltage and gate to source voltage, I have just discussed briefly how to get this IV characteristic. So this is how the graph is going to look. Right now, I will not derive these characteristics of your MOS device. I'll directly write the drain current in saturation. So once your drain MOSFET enters saturation region, which is the region when your drain voltage is greater than VD sat, which is VG minus VT. If your drain voltage is greater than this, your drain current is independent of drain voltage, and it depends only on the gate to source voltage, and it's given by beta n by 2 into VGS minus VTN the whole square. This is the only equation you will have to we'll be using throughout this course. Okay, so this is a very simplistic model for your MOS device, and in fact from 1960s we have already 6 decades had passed since then, and we have had a significant modification to the MOSFET's model, the mathematical model. Today it's impossible to use the ideal exact mathematical model of a MOSFET and perform hand calculations, so you have to rely on simulation softwares for it. Okay, so the decades of research has gone into it to capture a very accurate model for a MOSFET, which will closely match the measured results. So you are going to fabricate a chip and measure the IV characteristic that should match with your mathematical equations. Okay, decades of work has gone into it. Now the model is far more complicated, but as I told in the beginning of this lecture, we are going to go for the simplest mathematical model. This is called as a zeroth order MOS model. With this, we will be able to derive some intuitions, and that will serve as an initial guesswork, or it will give a guiding path for the designer when the designer is actually designing a circuit on a simulation software. Okay, so it will serve as a guiding path for you when you're designing your circuit. So which is why we'll start with these very simple equations. Okay, they may not exactly match with what you're observing in a simulation result or a practical result, in a measured result, but they will give you an idea of how the circuit will behave. Okay, so this is your drain current as a function of gate to source voltage. It is independent of drain to source voltage. To a first order, it is independent of drain to source voltage, and it has a square law dependence on the gate to source voltage. And that I said, this is the derivation for a long channel MOSFET. I said you can immediately see if it is obeying a square law characteristics by looking at the output characteristics. If you look at the output characteristics, as you increase your gate to source voltage, even though I'm changing my gate to source voltage linearly, you will start seeing a quadratic increase in your current. Okay, so take an example. Let's assume your VTN is 0.2. VTN is 0.2, and I'm changing VGS, say from 0.4 onwards in steps of 0.1. So this is 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. I'm changing it slowly from by 0.1 volts. At every stage, the current is proportional to let me call it as VG minus VTN the whole square. Okay. So let me give a simple, I think most of you have done 12th standard math, so you'll be able to see that. Let's assume that you have a function like this, which is square law function. So n plus 1 whole square minus n square. If I ask you to find the difference, what will be proportional to? Will it depend on the value of n? See, if I assume it's n, if it's a linear dependence, n plus 1 minus n, it has no dependence on the value of n, right? The change is always equal to 1. But now if I assume n plus 1 whole square minus n square, the change is proportional to n, right? It's 2n plus 1. 2n plus 1 is the change. So which means higher the value of n, more will be your change. So that's what this graph is telling you. This graph is telling you that as you increase the gate voltage, the change in the drain current will be more and more pronounced as you increase your gate voltage. Okay, so this delta I will be more than this delta I here. But delta V is same here. This delta V is same and this delta V is same. But as you increase your voltage, the change will increase. That's how you can read from a IV graph. Okay, output characteristics of a MOS device. So now, as we said, once you know the MOS characteristics, the two most important things for an amplifier that we need to understand is transfer characteristics and output characteristics. Once you know the transfer characteristics and output characteristics, then yeah, I'll add that. I'll include that now. Once you include transfer characteristics and output, once you know transfer characteristics and output characteristics, then we can derive a small signal model for a MOS model. We will know everything about the small signal model of a MOS device. From that, we can start building amplifiers using that small signal model. Okay. So this is your transfer characteristics. So which transfer characteristics is output current versus the input voltage. So the output current is the drain current versus VGS. For VGS less than VTN, the drain current is 0. For VGS greater than VTN, your drain current has a square law dependence. Okay, and the equation is given by half mu n Cox W by L into VGS minus VTH the whole square, VTN the whole square. VT is your threshold voltage of your MOSFET. Okay, mu n is the mobility. So you should understand this mobility is a slightly complicated word. I'll probably, I'll spend some time after this lecture, and then probably sometime I'll explain what that mobility is. So if you took an n-type semiconductor and applied a voltage across it, the conductivity of this n-type semiconductor depends upon mobility, right? It tells you how well can an electron move in the presence of a potential gradient. If you apply a potential gradient or a voltage or electric field across a semiconductor, n-type semiconductor, this mobility mu n tells you how well this electron can move inside that. But in a MOSFET, it's not a pure semiconducting region. It's actually surface. The electrons are moving near the surface. Okay. So here the surface contains, this is silicon dioxide, this is silicon. So there is this sudden change in the surface near the silicon dioxide interface. So that mobility will be slightly different from your bulk mobility. So this is called bulk mobility. If an electron or a hole were traveling in a semiconductor in the bulk region, that mobility will be different from the surface mobility. It will be slightly different. We'll talk about that a little later. Okay. I'll quickly finish this lecture and then I'll take 2-3 minutes and finish it. So if you look at the output characteristics, we said the drain current is independent of drain to source voltage and it remains constant. And in this region, we said the slope here, the output resistance is infinity. R naught, which is dou ID by dou VDS, the whole inverse is infinity. But in practice, what actually happens is that, probably I'll just explain it here itself using this MOS device here. What happens is that as you increase your drain voltage, your channel length will start reducing, right? The actual physical channel length will start reducing as you increase your drain voltage. Previously I said we'll ignore that, but now we can't ignore it anymore. The channel length will reduce. And the voltage across the channel is always fixed because any excess voltage is going to drop across, any excess voltage is going to drop across the depletion region. So the voltage is always fixed, but the channel length has reduced. Okay, so what happened to the channel resistance? Length is reduced. So what happened to channel resistance? It has reduced. Voltage is fixed. Voltage across the channel, this is fixed. The conducting part of the channel is fixed. And resistance of the channel has decreased. So what will happen to the current? It will increase. Resistance of the channel has decreased because L has reduced. So current will now increase. So what you will observe in a practical circuit, in a practical MOS device, is your drain current will increase linearly to a first order. It will increase linearly with the drain to source voltage. And the slope of this curve, inverse of the slope. So R naught, the slope of this curve, which is dou ID by dou VDS, it's called GDS, the drain to source conductance. So this GDS is what you will be seeing in your cadence software. So if you run your cadence software, you will actually notice this. If you do a DC operating point analysis, you will be able to read this parameter. Okay. So GDS, again, it's an incremental parameter. It will depend upon the quiescent VDS and the quiescent drain current. At that point, we estimate what is the value of GDS. And we will, when we use it in small signal model, we use the more popular term, which is R naught, 1 by inverse of R naught. The output resistance, which is the inverse of slope here. So R naught, which is given by dou ID by dou VDS, the whole inverse, is your output resistance of your MOS device in saturation region. So if you want to use a MOSFET as an amplifier, you have to use it in saturation region, in this region. And in this region, the output resistance is given by dou ID by dou VDS, the whole inverse. And the value of that output resistance, I'll just take a minute to explain this. So what you have to do to your conventional drain current, this is your drain current before channel length modulation. After channel length modulation, you just add a parameter, which is 1 plus lambda VDS. So this lambda is called channel length modulation parameter. We just modify the equation and write it as 1 plus lambda VDS. So now you differentiate this equation with respect to VDS. You will actually get this term, the whole term multiplied by lambda, if you differentiate this. So then I can write it as lambda into ID naught as GDS. So your R naught is 1 by this, you get 1 by lambda ID quiescent. We'll approximate it to the quiescent current. It's ID naught actually. ID naught is the drain current corresponding to VDS equals VDSAT. Okay. But we can approximate it to the quiescent drain current also. So your R naught is given by 1 by lambda IDQ. So we have just introduced one small signal parameter. Okay. So can I take an extra 5 minutes? So I'll finish up the MOS physics today's lecture itself. Is that okay? Do you guys have a lecture in the next class? Do you have a class now?
Yes, sir.
Okay. So fine. Probably I'll very brief. We don't need this for our tomorrow's lecture. I'll anyways upload the recording today. So if you have a class, you can leave. I'll just take 5 minutes to explain it. You can watch the video. It's only 5 minutes of extra content. Yeah. Okay. So now I'll just quickly discuss some second order effects. Now in this course, we will not be considering the second order effects. We will mainly focus on the first order effects, which is your channel length modulation and the conventional square law equation. That's it. Those are the equations we will be using throughout this course. The second order effects, the additional effects, there are only two major effects. I'll just discuss this so that it will help you in your lab, in your lab exercises. So first thing, the first second order effect is called mobility degradation. The mobility degradation happens, what happens is that as you apply a large gate voltage, as you keep applying a large gate voltage, the electrons will be drawn closer and closer to the semiconductor, silicon oxide interface. So you have silicon here, which is your p-type semiconductor, and this is SiO2, silicon dioxide. So these electrons will be drawn closer and closer to the interface between semiconductor and oxide. Now, as these electrons are drawn closer, I told you guys these electrons are not the same electrons in the bulk of a semiconductor. When the electron is in the bulk region, they undergo drift. The mobility is very different from the mobility that these electrons experience in the surface state, near the surface region. When these electrons are brought closer and closer to the surface, this silicon SiO2 region will offer more resistance for the flow of electrons. Okay, it's not a smooth surface as it is in the bulk region, so the surface will be rough, rather, because there is a discontinuity in the region from silicon to semiconductor oxide. So these electrons will experience some kind of additional resistance or a degradation in mobility compared to an electron traveling in the bulk region. So that reduction in mobility will further increase if the electrons are drawn further closer to the surface. And they will be drawn further closer to the surface if your gate voltage is much greater than Vt. So this degradation in mobility is modeled. So if your mu is your mobility at low gate voltages, we model the degradation in mobility by a parameter called theta. It's called mobility degradation parameter. It will be mu into Vgs minus Vtn. So instead of mobility, you will replace it by the degraded mobility given by this expression. Okay, this expression tells you that as you increase your gate to source voltage, your mobility decreases. Okay. Yes, this is purely because of the vertical electric fields, because of the gate to source electric field, gate to bulk electric field. The electrons will be drawn further closer to the surface, and that surface roughness will decrease its mobility. So that's called mobility degradation. So what happens to your IV characteristics is your IV characteristics will look something like this. Okay, it will be your typical drain current divided by 1 plus theta into Vgs minus Vtn. So theta here is called mobility degradation parameter. Okay, see what happens is there are two things. If your electric field is very high, you will be drawing your electrons very close to the surface. Okay, if your electric field is very high, you draw electrons closer to the surface. What does electric field depend upon? It depends upon the gate voltage. Does it depend upon anything else? Does it depend upon the thickness of the oxide? It also depends on the thickness of the oxide, right? Yes, no, it will depend on, right? Voltage V by, that will depend on thickness of the oxide, right? The electric field will also depend upon thickness of the oxide as well. So which means, as you see, typically the oxide thickness will be in the order of few nanometers. If you see today's mass technologies, it will be in the order of few nanometers. Okay. So when we go to lower technology nodes, oxide thickness also reduces, which means that will increase your field and that will increase your mobility degradation effect. So you will notice mobility degradation as you go to lower technology nodes. Because of which, what is the effect of it? So your IV characteristics is now modified this way. So your drain characteristics is modified this way. What is the effect of this? At very high VGS, at high VGS voltages, can I say instead of square law, it will be a linear dependence on VGS, because this term is going to dominate. So it will cancel out one VGS minus VT term. So you'll have more of a linear dependence on the gate to source voltage. So shown here, if you see here, this graph captures both the output current. Here I have not shown channel length modulation. Okay, so that's why this drain current is independent of VDS. Initially for small VGS, if you see, the delta I here is more than the delta I here. So it's obeying square law characteristics for small VGS. But as I increase my VGS, you see here, the change in the current is linear. The change in the current is delta I here is linear with the gate to source voltage. So this captures the mobility degradation effect. Okay. If you want to include channel length modulation as well, channel length modulation can still exist. Okay. Yeah. So let me finish this. So if you can actually include channel length modulation as well. If you include channel length modulation, you'll have to add 1 plus lambda VDS to it. So in that case, the graph will look something like this. This is a more exhaustive graph. So this is your channel length modulation included. And after a point, I discussed in the previous lecture, after a point, if you keep increasing your drain voltage, the drain to source, so you have N plus is your drain region, your bulk is P10. There is a diode here, a PN junction diode formed between drain and bulk. That diode will keep getting reverse biased, and at some point, the diode will break down. So what kind of diode breakdowns exist? What are the typical diode breakdowns? One is an avalanche breakdown. What is the other kind of breakdown? Zener breakdown. So there are two kinds of breakdowns which happen, avalanche and Zener breakdown. So this will be one of those breakdowns, whichever is a smaller value that will determine for this P plus N P N plus junction, that will be your breakdown, and your current will suddenly, a large current will start flowing from drain to bulk. Okay, bulk and source are shorted, so there will be a large current from drain to bulk. It's not the channel current, but this current is actually a current through a diode, the diode which is undergone breakdown. Okay, so this is your typical IV, a second order characteristic, IV characteristic, which has captured everything, both mobility degradation and channel length modulation and breakdown. So this is the complete IV output characteristics of your MOS device. Now, the final thing that you need to keep in mind, or rather which we have to analyze, is short channel effects. So previously we said the IV characteristics change because of the vertical electric field. EY is your, this is your y-axis, I have shown it here, this is y-axis and this is x-axis. The second electric field is your lateral electric field or your horizontal electric field or the drain to source electric field. Now as technology is scaling down, your channel length is decreasing. As your channel length decreases, the horizontal electric field will keep increasing. Right? If the voltage is remaining same, more or less the same, and the channel length is decreasing, your horizontal electric field will increase. So as your horizontal electric field increases, the whole reason why conduction happens, the physics behind the conduction in a MOSFET is drift of electron in the channel. When electron drifts, it undergoes, that's the reason why you have drain current. But when the electric field becomes so high, you will expect, if the higher the electric field, you will expect higher the electron velocity. But what will happen, I think if you have studied the basics of drift, you will know that as you increase your electric field, you will expect your drift velocity, the velocity of the electron, to also increase. Right? So this is something we have already discussed in the beginning of the lecture, beginning of this course. I said if you take a semiconductor and apply a voltage across it, there is an electric field present from here to here, so it will drift the electrons from cathode to anode. Okay, so this electron drift, the speed with which this electron will move is proportional to the electric field. The drift velocity, the speed with which this electron will move, is proportional to this electric field. So if I increase the electric field is going to impart more and more kinetic energy to the electron. Because its velocity is increasing, it's going to impart more and more kinetic energy. But understand, this is a semiconductor lattice where the electrons are traversing. So these electrons are also undergoing collisions, constant collisions with the lattice. After a point, if you keep increasing the electric field, any excess energy the electric field gives to the electron, any excess energy the electric field is imparting to the electron will be absorbed by the lattice. So that won't contribute to the increase in electrons energy, but rather the lattice will start absorbing it. Okay, so typically that happens, there is a minimum distance an electron travels before collision. If the electric field becomes so high, then the electrons will undergo so many collisions that your electric field will no longer be able to build up the velocity. So any excess energy the electric field is imparting is absorbed by the lattice. Okay, and it will be dissipated as heat and all of that. So the electron velocity will remain saturated, it will remain constant after a certain field. So ideally you would expect the electron velocity to increase like this, but the electron velocity will saturate. So this is called the critical electric field. And the drift velocity where it saturates will be of the order of 10 power 7 centimeters per second. Okay, see, generally we invoke relativistic effects when the speed approaches speed of light. Is it close to the speed of light? 10 power 7 centimeters per second? What is the speed of light? No, speed of light is 3 into 10 power 8. So that is 3 into 10 power 10 centimeters per second. 3 into 10 power 8 meters per second, or 3 into 10 power 10 centimeters. It's nowhere closer. It's 3 orders less, right? It's still much lesser than the speed of light. So this is the typical saturation velocity in your semiconductors, which will be in the order of 10 power 7 centimeters per second. Okay. So now, when your electron velocities reach this point, your current current between drain to source will no longer depend upon the drain to source voltage. Okay, so now the thing is that the current here depends upon the channel charge. So which is your, I'll not derive the expression, so I'll directly tell you that the channel charge is proportional to VGS minus VT. Okay, and your drain current is because of drift. So this is, if you write the exact expression for your channel, I have given us very quick derivation for this drain current in case of short, when you have to include short channel effects. See this, I have assumed a small model for your surface charge region. Consider a small region dx and let A be the area of cross section. So this is y axis. So this is W is the width. So the cross sectional area is W into y times dx is the volume of this region. Let Q be the charge enclosed in this region. Then that divided by Wy dx will be your charge density. This is your charge density. This is number of charge per unit volume. Okay. Now what is the surface charge? What is the the Qi? When I write Qi, I am referring to the surface charge. See, recollect, keep in mind what is the surface charge is that this is your gate voltage. Okay, this whatever charge Qi is present here, you will have minus of Qi present in this region. So to get the surface charge, that will be nothing but the area stored under with the charge stored on this area. Okay, that's your surface charge. Okay, charge stored on this area divided by the cross sectional area of this region. So if I use that, what is the cross sectional area here? The cross sectional area of this region, can I say it's W dx? Yeah, so it's W dx. So this I can write it as Qi, the inversion charge, divided by y. Qi, W into dx is the area, Q is the total charge, divided by W dx, that will give me the inversion charge, which is charge per unit area. Okay, inversion charge units is charge per unit area. So now I'll write it this way. Your current is given by dq by dt. The total charge here is, let rho, which is your charge per unit volume, we said it is Qi upon y. So it will be, this is charge per unit volume. Okay, Qi upon y. And if you see the volume is nothing but Wy into dx. This is your volume. Multiply by this, you get your total charge. Now if you differentiate this, d by dt of this entire term, I get the current, right? So if I take Qi common out and W common out, y and y cancels out, you will be left with dx by dt. What is dx by dt? The horizontal velocity in the horizontal direction. What velocity is that? That's your drift velocity. So you get the interface charge, inverted charge times W, the channel width, times dx by dt. That is your drain current. And if dx by dt is your nothing but your drift velocity. So Qi W into drift velocity is Vd. Now when you attain saturation, when your horizontal electric field is so high, then the drift velocity will become a constant. Otherwise, it would have depended on Vd sat, which is also equal to Vgs minus Vt. So that's why you get the square law dependence. But right now, it has no such dependence. It is independent of Vd sat, Vds, and rather it will be simply V sat. I've written it as V sat. So if you write this expression, your inversion charge is given by Cox into Vgs minus Vtn into W into Vd sat. That's your drain current. Now your drain current is proportional to Vg minus Vt when the device enters short channel regime. So this is the effect of short channel. When you go to short channels, very short channels, because of velocity saturation, your drain current will just be proportional to Vgs minus Vtn. Okay, it will have no more dependence on Vds, and it's no longer a square law characteristic, but it's a linear characteristic. So that's it about the physics of the MOSFET. In the next class, I'll start from here and derive a small signal model. Okay, and then we'll also compare it with bipolar junction transistors.